All right, welcome back. So we're going to talk through the homework component of this. Hopefully you guys just watched the video or videos on the types of radiation, so alpha, beta, and gamma radiation. And then I just want to kind of explain to you in person what this assignment is going to be. We're going to split it in two. It seemed like too much to do all at once. So your homework is going to be to start this HMH book that we're going to look at right now. And it says here in big and red, only go through decay. Don't do the fusion fission. I'll show you where that looks like. So we're going to just talk through coming to some potential answers, and then the part of this is a table that's really important to understand, and that would be something that we'd look at on a exam down the road of really understanding how those pieces look. So let me pull that up, and then we'll talk it through and go from there. Okay, so you're looking at exploration 2, changes in the nucleus. Again, you'll find this in your assignments page. So when we have this, we're going to talks about the radioactive decay. It starts with your alpha emission, which we know we're basically losing this helium molecule. So we have this unstable element that's trying to break into a more stable element, and it's emitting this alpha particle, which is just helium. And so it's talking about, if we look at this image up here, describe how the nucleus changes. Does it become more or less stable? Is energy taken or released? And then what would that energy be equal to? So a possible answer for that is it's becoming more stable, right? Things aren't going to tend to be less stable by emitting the 2 neutrons and protons, which is transforming it into thorium-234. All right, it has to release energy, and if we were to look at this because it's a spontaneous component, right? There's no energy input. We could also look at those mass balances and figure out the difference using E equals mc squared. So it's equal to the mass deficit by looking at basically what we had the mass before and we have the mass after, if we were to take the masses here and there. All right. Then we talk about beta emission, which is this idea of we have an imbalance in protons and neutrons. So we have either neutrons becoming protons or protons becoming neutrons, and they're going to emit either an electron or a positron to make that happen. So we can see here, right? What we have is I have these 2 protons, and then this guy's sitting up there that turns positive. The way that it's going to do that is basically release that negative charge. So this is emitting that negative, that electron charge this is going through. That's that beta decay model. All right, we can also have it be the reverse. If we have too many protons, we would release that positive charge. So it's going to talk about, you read through it, and considering that diagram, what's changing in the nucleus? Does it become more or less stable? All right, well, it's going to become more stable by becoming nitrogen-14. And the way that it's going to do that, again, is by looking at changing the atomic number, so the number of protons that it has. Instead of going from 6, it goes to 7. The atomic number of protons are what determines the element. And so, again, we could look at the energy released. We could find that mass balance and go from there. All right. Then we have our gamma emission, right, where we have this excited state of plutonium, and we can see that we're not changing our masses. So this gamma ray is an electromagnetic ray. It has no mass, but it has a lot of energy that is based on its frequency and Planck's constant. So we see that the masses are still going to balance up, and that they are our most damaging ones. So we look at the diagram in plutonium-240, and we want to describe how the nucleus is changing. Well, we know that that nucleus isn't changing, right? But it's becoming more stable by emitting that extra energy. So the energy is the energy of the gamma ray, and then we can figure that out basically with those excited states. Okay. This is the chart that I really want you to pay attention to. So if you can understand this and if you get it all right, then that's great. So you should really try this on your own before you just look at the solutions of what's going on. So what we want to figure out is the types of emission, and then we have what's happening to the ratio of neutrons to protons, and then the atomic number, which is the number of protons. So if I emit an alpha particle, right, we're breaking it into those 2 different molecules, and those 2 different elements. We have the helium, and then we have whatever it was before, right? So the ratio here, right, that we have, if we have that mass difference, is what we're going to see is we'd see a difference in the nucleus. We've lost the helium, basically. Those protons are gone. The beta particle, all right, where we are emitting, right, the negative, what that means is that if we have this ratio decreasing, right? So we're emitting the negative value, which means basically we're turning a neutron into a proton. So we had that piece that was bound together with a positive negative. We release that electron, and then we're going to get more protons, which is going to move this number down. The positron is the opposite. We have a proton that's releasing that positive charge as a positron, which means we have a proton turning into a neutron. And so the larger number on top makes this go up. And then the gamma rays are unchanged. So if we look at the answer to this, right, our atomic number, which is the number of protons, is decreased by 2 because they're in that helium molecule. And then we have the beta particle. The atomic number is increased by 1. We have more protons, right? We have a neutron that's becoming a proton, which gives us more protons. Positron's the opposite. We have a proton becoming a neutron, so our atomic number goes down. And then a gamma ray doesn't have anything to do with the number of protons and neutrons. It's back to this picture up here, where you have that electromagnetic radiation that is thrown off. All right, you're going to stop at that point. You can pick it up on Monday. You don't need to do this component yet. We will come back to that on Monday and talk about fission and fusion and how these go together. I'm also going to try to hopefully find a something you guys can do that's hands-on with this. Obviously, we can't go and mess around with protons and neutrons very easily. But we'll try to find something that you guys can do that's not just listening to online videos, and hopefully make it a little bit more dynamic. All right, hope you guys have a good weekend, and that all is well. And I will touch in with you on Monday and go from there. All right.